I mean, I'll remember it every time. All right. So last time we were doing chapter 23, I think it was. Uh, yeah, chapter 23. And we were working through voltage. So now I want to show you sort of the last bits about voltage. Last time we were covering basically point charges and stuff of that sort. I'll leave that part up to you, like where you're making an assembly of particles, bringing them together. So you start off, you have one particle here in space, and you bring another particle out from infinity next to that, and then another particle out from infinity next to that, and so on and so forth. Your book does a good job going over that, and that's pretty remedial stuff. The big thing you got to watch out for there is when you start making a formula like that, it's really easy to count things twice because you're trying to, use some kind of logical way to make sure you get them all. So you'll say, well, one's got a group with 2, and then one's got a group with 3, and then one's got a group with 4, and then one's got a group with 5. Well, when you get to 5 later, you're going to say 5's got a group with 1. Well, you already did 5 and 1. So I'd say keep an eye on that when you're doing it. But other than that, it's pretty straightforward problem. All I have left is basically to show you how to do the more difficult aspects of the chapter, which is, that and the dipole thing. But the more difficult aspects of the chapter is where you're actually using integrals to calculate voltage, electric potential, if you will, near an object. So it's not like Gauss's law where you had to have this high level of symmetry. And it's actually a little easier just because you're actually using the scalars. So I'll go ahead and get started with an example on that. Does anyone, we only got 3 people in here. Does anyone have any questions before I start? Okay. I already told Kristen this, but anyways, I had mentioned earlier about the Schaum's outlines, SCHAUM' outlines. You can Google that term, and they have one, physics for scientists and engineers, which is basically for our university physics class. As you can tell, our textbook's called Physics for Scientists and Engineers. They also have one that's called college. That's called college physics. And actually, I prefer the college physics one, but it doesn't cover the calculus-based stuff. So really don't buy that one unless you can buy 2. Okay. Because you definitely need the physics for scientists and engineer one. There's also like a applied physics, there's a beginning physics 1, beginning physics 2, and then there's just like a physics problem solver, also by Shams, and another one by REA, where it's literally just got 5,000 or 6,000 problems solved. Those are good things to have if you're looking for more examples beyond what the book and I give you. And I was telling Kristen a second ago as well, that the examples I do are more or less parallels, if not exactly the same as the examples in the textbook. But that's mainly because there's a limited number of examples you can really do. without using a computer, writing code and stuff like that. So at least in some of these chapters, you only have one choice or a couple of choices to do. But anyways, the other thing about those Shams outlines is it turns out you can buy used copies for really cheap. I was celebrating them to a student last night and pulled them up and found a couple copies for $4.95 a piece. Now they're cheap to begin with, like normally $15-16, something like that, but now you can buy a used one at $4.95. That might be, you know, price effective for you. So anyways, just wanted to let you guys know that. What I'm first going to do is I'm going to work calculate the electric potential above the center and along the rotation axis of a ring of charge. So I'm going to go ahead and share my screen with you guys, and it has worked twice now, so hopefully it's still working. And I do this. Yes, it worked. Woohoo, who's your daddy? All right. So what I'm going to do is I'm going to draw an oval. Actually, I probably should have left that, but this program will actually make it really nice if I do it right. So I'm now going to go from here to here, from here to here, and from here to here. And now I'm going to point out something that you have to know, but is maybe not all that necessary right now. But when you make a coordinate system with 3 dimensions or 3 axes, it has to be a right-handed coordinate system. So I don't know if I've told this class that or not, but I wanted to reiterate it. You can imagine it with you holding up your right hand, like you're holding right here. Your index finger is the positive x-axis. Your middle finger could be the positive y-axis, and then your thumb, again, this is all with my right hand, then your thumb points in the direction of positive z-axis. If you find that the x and y are right, but the z is pointing downward, then you've got a left-handed coordinate system. And basically that makes your math work out wrong. So you'll have like errant cross products, determinants, stuff like that. So just make sure you do that. That's about all I'll say about that. So now what we have here is a uniformly distributed charge, elliptical, or excuse me, a circular charge. Actually, let me put this back on that special thing. And is very thin, like we can assume its thickness is like dr or something like that, an infinitesimal amount. And it's centered on the origin, and we're looking for the actual, oh, that really messed up. We're actually looking for the voltage, the electric potential at that point, a distance z above the axis that the plane is in. It is uniformly charged, so that means there exists a certain amount of charge, lambda, which is equal to dq over dl, and it has a radius. Whoa, that was really bad. Well, yeah, okay, that's much better. A radius that I'll call r. Okay. So that's really all you need to know. Now, if you think about it, the lambda being a uniform charge per unit length, that means that if you take any, let's say, millimeter long portion of this ring of charge and determine the charge on it, any other millimeter long portion will have the exact same charge. So if you think about that, then the total charge Q, which is what I'm going to put here, is actually equal to Q over 2 pi r. That's what the charge per unit length is, because the length obviously is 2 pi r, and the charge is a total charge of Q. So that's just one of the times where I can very concretely give you exactly what the charge per unit length or charge density is. So I just took the time to do it. And I'm not happy with my writing right now, so I'm obsessing about it. All right, so we want to know that. Now, what we have is that dV is equal to the integral of dq over 4 pi epsilon naught R. Now that's the key thing to realize here. So when we did Gauss's law, or excuse me, when we did Coulomb's law, we had F equals Q1 Q2 over 4 pi epsilon naught R squared. Then we tried to get rid of that action at a distance by imagining there exist fields. And what we did is we divided out one of those Q's and acted like the remaining Q was the one that was creating an aura around it, and the other Q was being affected by it. So that became Q over 4 pi epsilon naught R squared. In other words, the only difference was 1 Q instead of 2. And now that we found the voltage to be an integral of E dot dl over some distance, when we found that, we found out that the charge or the voltage is basically Q over 4 pi epsilon naught times R to the first power. So that's something to keep in mind, just to keep your wits about you, keep you from making careless mistakes, because it's very easy to accidentally write R squared there or write 2 Q's there or something. So there's our formula that we use when we got a distribution of charges. So I'm going to say V is equal to the integral of dV, and that's going to be equal to 1 over 4 pi epsilon naught times the integral. Now lambda is actually going to be the charge per unit length. So dq is going to be equal to lambda times, now I'm going to use what we recall from trigonometry. If I allow R to basically stay the same, but allow the angle to change by an amount d theta, then the length of that would be r d theta. So I'm now going to say this is lambda times r d theta, and that's what goes up here, lambda r d theta. And remember, lambda has units of coulombs per meter, so lambda times r has units of coulombs, and d theta has units of radians, so that is a non-unit basically, because it comes from s equals r times theta, where theta is a length divided by length. And then all I have left is the distance between the differential charge element, which I'm showing right here, is dq. Okay, so that distance, as you can tell, is actually the square root of z squared plus r squared. Now the good thing is, in reality, we're only integrating with respect to theta, so everything's a constant essentially, and we get lambda r over 4 pi epsilon naught square root z squared plus r squared times the integral d theta from 0 to 2 pi. So ultimately, I think you see we're going to get lambda times 2 pi r over 4 pi epsilon naught times the square root z squared plus r squared. Any questions on that? Now you can actually leave it like that, but you can also get it in terms of Q, because you can probably tell that lambda, since lambda is actually equal to Q over 2 pi r, lambda times 2 pi r should be just Q. So we can write that also as Q over 4 pi epsilon naught times the square root z squared plus r squared. Okay, so that was our first one, and that's a pretty straightforward, easy integral problem to solve. Now, the one thing I mentioned to you about when we switched from Newton's laws of motion, where we had to use F equals ma, and everything was in terms of vectors, then we went into energy considerations, and everything was a scalar, and it made it easy. But I told you that, you know, you could then take, since the velocities were really easy to find in conservation of energy, because, you know, you always had a kinetic energy 1/2 mv squared, so you could find the velocity, but the accelerations were hard. Whereas in Newton's laws, the accelerations was what you easily came up with, because it came straight from F equals ma. but then you could use kinematics to get, things like velocity after a certain amount of time. Well, here is the opposite way around, or excuse me, when you go to the energy methods versus the vector methods, they're sort of the opposite way around. So the same thing here, I now have scalar method, but I can't get something like the electric field very easily. I can get the electric potential, but I have to do another thing to get the scalar or get to the electric field. So that's what I'm going to show you now. It turns out that when you have certain conditions true, then one of those conditions true means that all the conditions are true. So I'm going to diverge for a second from what we're talking about and go to this more general, great mathematical fact that's been discovered. So one, if you take this vector operator called del, okay, and you cross that with, say, E, and it is identically 0, okay, then this is a conservative field. Okay, and conservative means you can make a conservation law with it. Okay, so that's a big deal. And this quantity right here is called the curl of E. It's also, some people call it the rotation of E, others call it del cross E, but the main thing is, if you calculate this for electric field, and it's not just 0 for a particular choice of X, Y, and Z, but it's 0 for all X, Y, and Z, then it's what's known as a conservative field. If that's true, then this has to be true too. Specifically, that tells us that an integral from A to B of E dot dl, in other words, a line integral from point A to point B, is going to be equal to just some FB minus FA, and is independent of path. So you can actually make up the easiest path you want and just use that, and that'd be fine. That's what that's telling you. Okay. It also means that the closed integral of E dot dl, in other words, you do a line integral that starts and stops on the exact same spot. I think you can tell from the line above that clearly means this is going to be equal to 0. Because obviously, if it's f of B minus f of A and B is A, then you're going to get f of A minus f of A, which is 0. Now, there's another thing that comes from it. Again, any one of these being true means all the others are true. Another thing that's up there is, and I'm going to use some mathematical terms just so you can experience them, but this upside down backwards E means there exists a scalar field V. That little symbol means such that E is equal to the negative gradient of V. Okay. And if I remember correctly, there's also this little thing about exact differential equations, but because I have not refreshed my memory on that recently, I don't want to jump into it, but it's something along the lines of realizing that dE is equal to the partial of E with respect to X times dx plus the partial of E with respect to Y times dy plus the partial of Z of E with respect to Z times dz. And because general functions that can take two derivatives, the order of the derivatives doesn't matter. So the partial of E with respect to X, then the partial of that with respect to Y is the same thing as partial of E with respect to Y, followed by the partial of that with respect to X. And when you have that, you have a very specific type of differential equation and a nice little trap or technique that you can use to get it. I think that comes from it too, but again, I haven't looked that up, so I don't want to just blatantly say that. Your book does tell you this somewhere in the book, but it doesn't express that either way. But we'll just leave it at that right now. So if you have a curlless field, then it's a conservative field. And that means there's a conservation law that can be used. If you have that, then by automatic, it's automatic that you have all these other things, which means the line integral, which is basically like the work done from A to B, is independent of the path. And a closed line integral, in other words, anytime you start and finish on the same spot, is going to be 0. And there exists a scalar field that you can represent E by. So that's the big thing here. And that actually gives us what I was talking about before I went to this, divergence from what we were talking about. I was saying, okay, now that we call it voltage, how do we go about computing what the electric field was? Well, this electric field is this voltage is a very special voltage. It's the voltage along the symmetry axis. And it's a voltage that depends only on the variable z. It doesn't depend on the variables x and y. And that's partly because x and y are both 0. If I went off axis, it becomes a really insolvable problem without some heavy duty programming. So now I can test this. I can use E equals negative gradient of V and calculate the electric field, and lo and behold, we should get the same electric field that we got in chapter 21 when we did this. But I want to make a little note here right quick to let you know what del is. So this del operator, for some odd reason, I know that in Brazil they call that nabla. So in Portuguese it's called nabla. I don't know why I know that. I actually know why I know it. It's just a goofy little tidbit. So it's I hat times the partial with respect to x, and then nothing. There's literally nothing. So whatever you put to the right of this, that derivative with respect to x is going to act on. And then you have a plus symbol, j hat partial with respect to y. Again, nothing next to it. And then you have a plus k hat partial with respect to z. Now that's just it in the Cartesian coordinate system. And vector calculus is all about converting vector, and tensor calculus is all about converting these things from one coordinate system to another. And if you took a junior senior level electricity and magnetism course, when you'd open up the textbook, the inside cover would have this nabla, this gradient operator, this del operator. It would have it in spherical coordinates. It would have it in cylindrical coordinates as well. So that's the deal. Is if you ever have to use a coordinate system other than x, y, z, then you're going to have to look up that or learn enough vector calculus to compute it yourself. And that's a worthwhile, fun thing to do. So I wanted to show you that. The other thing is I wanted to show you that del cross E, exactly what that is you're taking a determinant of a matrix, the first row of which is I hat, j hat, and k hat. And I'm going to use an abbreviated way of writing this. I'm going to say partial with respect to x is the first entry in the second row. Partial with respect to y is the second entry in the second row. Partial with respect to z is the third entry. And then E sub x, meaning the x component of the E field. And then E sub y, and then E sub z. So that's actually what that curl is. That curl or rotation. Okay, and it does. It's a vector operator that tells us whether the field is one that sort of curls around, say, a sink or a source, or if it's one that radiates or diverges out. In fact, there's another operation with the same operator, del dot E, that is called the divergence, and that one tells you whether things are radiating out from a common point or in from a common point. So those are the two things that it turns out that are needed to fully specify a vector up to the addition of a constant vector. All right, so that's all that. So now let's take this result, which is Q over 4 pi epsilon naught. So we got V equals Q over 4 pi epsilon naught square root z squared plus r squared, like that. And we're going to calculate E sub z, which is equal to the negative. Now we're actually doing a full gradient, but there's no x in here. So the partial with respect to x is going to give me 0. And there's no y in here. So the partial with respect to y is going to give me 0. There is a z in here, but I'm talking about the component, not a vector symbol. So I'm going to leave off the k and just take the derivative with respect to z. So I'm going to pull out all the constants, which are q over 4 pi epsilon naught. Notice the negative came as part of the formula. So now I'm going to say partial with respect to z of z squared plus r squared to the negative 1/2 power. Now, a derivative of something to the negative 1/2 is, of course, negative 1/2 times the thing to the power it had minus 1. So it had a power of negative 1/2. When I subtract from that 2 halves, I get negative 3 halves. And now I've got to apply the chain rule and take the derivative of what's inside of the root, which is z squared plus r squared, and the derivative of z squared plus r squared with respect to z. Notice I'm just pretending like all the other numbers are constants. The derivative of z squared plus r squared with respect to z is just 2z. So you can see the 2's cancel out. You can see the negatives cancel out. So E sub z, which is really the only electric field we counted before as well, is actually equal to, once this cancels out with that, and once this sign cancels out with that sign, we get QZ. Well, let me stick to my color I was using. Whoa. I get Q times Z over 4 pi epsilon naught Z squared plus R squared to the 3 halves. Okay, so that's supposed to be the answer. And in fact, if I stop sharing for just a second and go back and let's say we're going to share a part of the textbook, we can do that. All I have to do is go to My Lab and Mastering, and then click on Open My Lab and Mastering, and then click on eText, and then wait 14 hours for it to load. I'm going to attempt to do that in real time. So let's pray for the best. So I'm saying no, I'm saying Pearson eText. It says open my e-textbook. Y'all aren't looking at the screen right now. I haven't shared the screen yet. Okay, now I'm going to go ahead and share the screen, and I'm going to say share screen. It looks like it should be probably this one, I guess. Okay. I don't want the desktop though. Oh, I want that one. That's weird. It just all of a sudden told me that it won't share it. There might be something they're protecting. Let's see if I can do something else. It actually did come up. Okay, so let's see. Okay, are y'all looking at 23-7 E determined from V from the book?
Yes.
Okay, that's cool. So I'm going to turn back to chapter 21, which is the first place we did this. And I'm going to do scroll down to electric field calculations for continuous charges. And I think you will see that we got Q times X. Notice I'm using Z and they're using X. So that should be the same. Also, they're using A for the radius of the ring, whereas I'm using R for the radius of the ring. So there's their A, and they're saying this distance away is X. So you can see this formula is exactly the same I had, except I had QZ over 4 pi epsilon naught Z squared plus R squared to the 3/2. So that, in fact, is exactly what we wanted. And now I'll stop share and I'll start sharing again so you can verify that that's exactly what we got. And you can see now QZ over 4 pi epsilon naught. So yeah, that's it. We actually can do what I claimed we could do. We've made a scalar potential. We can take the negative gradient of that scalar potential and get the electric field out, and we just verified that. So any questions on that one? Okay, so we have another problem now that we want to try to work. And in this case, I'm going to work one using this result to some extent, but I'm going to work it in this case for a disk, a circular disk of charge, as opposed to a ring of charge. So in this case, what do I do? Okay, so I'm just trying to pull it up to the book so we can be in the right area. So now I'm going to say that I have a disk of charge, and it's oriented in a coordinate system like such. And this is the z-axis. Again, I would like to know the electric potential at that point above the center along the symmetry axis of this disk. The total charge of this disk is Q, and it's uniformly distributed. The radius of this disk is R. And I will say, since it's uniformly charged, I'm going to say that the charge per unit area, sigma, is just Q over pi, pi R squared. Okay. Now, why do I do that? Well, this is one of those cases where we're going to use a differential volume element, or in this case, a differential area element. And I am going to do that in red. So I'm going to draw a little differential area element. And the width, or thickness, if you will, of that area element is going to be dr. Okay, and the radius, of course, of that little inner part is going to be just R. And I'm going to argue that that differential charge element, dq, is in fact equal to 2 pi R dr times lambda, or excuse me, not times lambda, times sigma. And I shouldn't have put that sigma. I should have put that sigma earlier, but I didn't. So, oh well. All right. So that's the charge element dq, 2 pi R dr. You could actually make this a little easier on us by finding how much charge is actually in that little ring. And what we're doing here really is we're taking the area of a circle of radius parenthesis R plus dr, close parenthesis. So that area of that circle would be pi left parenthesis R plus dr, right parenthesis squared. minus the inner radius, minus the area of the inner circle whose radius is r. So that'd be minus pi r squared. And what you see when you get that is all those terms disappear except for the 2 pi r dr. And they disappear strictly because the other terms are like dr or dr cubed. They're actually just dr squared instead of just dr. So they're dr squared, dr cubed, that sort of thing. Whenever you're dealing with dr and you have a dr squared, you can assume that dr squared is negligible. And that's what we did there. So I can go ahead and use the fact that v is equal to the integral of dv is equal to the integral of dq over 4 pi epsilon naught r. Okay, so I'm going to say my solution is as follows. I can say, for instance, that dq is equal to 2 pi r sigma dr. But if we realize that sigma is a constant, that tells us that q over pi r squared is equal to dq over 2 pi r dr. And you don't even have to use the sigma. You can say that, notice this pi is going to cancel out right here. And this will give you that dq is equal to, let's say, q over r squared times 2r dr. Okay, so I can just replace that instead of using the 2 pi r dr. I haven't done anything. It's just made it where I don't have to go back and substitute the real value of sigma in later. So now I can put that in. I think you can see in some weird way that the distance r is equal to the square root of r squared plus z squared. Okay, and I'll probably write that in the other order, so it'll be like the other one. I'll have z squared plus r squared, but that's enough for right now. So I'm going to say v is equal to, let's pull out all the constants. I'm going to say the constants are 2q over 4 pi epsilon naught. And then I've got left inside r a dr over the square root of z squared plus r squared. Okay, now just when you think this might be a horrible problem and you have to use a trig substitution, you're lucky that you don't, because there happens to be an r in the numerator. So I can say let u equal z squared plus r squared, so that du is equal to 2r dr. Okay, and not only that, I already have a 2 right here, and I have an r and I have a dr. So I've got everything I need. And what's going to happen now is I just say equals q over 4 pi epsilon naught times the integral of u to the negative 1/2 times du. Does that make sense to everyone? I haven't put the range of integration, but I think y'all can tell when we were integrating with respect to r, the range of integration would be from r equals 0 to big R. So I'm not going to do that until I substitute the z squared plus r squared back in. But this is a fairly trivial integral. The integral of u to the negative 1/2 is just, in this case, we're adding to the exponent. We're going to add adding to the exponent, which will go from u to the negative 1/2 will be u to the negative 1/2 plus 2/2. So it'll be u to the positive 1/2. And then I'm going to divide it by positive 1/2. And that's the same as multiplying by 2. Okay. So I'm going to get 2 on the top, q over 4 pi epsilon naught. Now I have z squared plus r squared, And now I've got to evaluate that from R equals 0 to big R, which I couldn't have made that uglier if I tried. Okay, does everybody follow what I did? Did I make any mistakes?
Isn't there supposed to be a negative?
No, because remember with integrating, you add 1 to the exponent and then you divide by the new exponent. So when we added 2/2 to -1/2, it became positive 1/2.
Oh, right.
Okay. So in this case, we're now going to say the 2's are going to cancel. The 2's going to cancel out with 4. So I got Q over 2 pi epsilon naught. Now I'm going to evaluate this at R equals 0. And of course, at R equals 0, I get basically just the absolute value of Z, because it's Z squared under the square root, but that square root's an absolute, is a positive root. So I'm going to say absolute value of Z, and then I'm going to say minus square root Z squared plus R squared, like that. And that turns out to be the actual voltage at a point Z along the symmetry axis, a distance Z away from the plane. Again, we might want to actually think about what this is in terms of the electric field. So E sub Z in this case should equal negative partial with respect to Z of that V. So now I could pull a negative. What I'm going to do is actually change the order of that. And I'm going to say this is just Q over with no negative 2 pi epsilon naught. And now I'm pretending like the square root comes first, because that's how I got rid of the negative. So if I take the derivative of Z squared plus R squared to the square root power, then basically I'm going to get a negative, because it's a negative in front of the square root. I'm going to get a negative times 1/2, and then I got to subtract 1 from negative 1/2, or excuse me, from 1/2, and I'm going to get, actually I'm going to subtract 1, right? Yeah, so it's 1/2, and then when I subtract 1, it's going to become negative 1/2. So it'll be minus 1 over Z squared plus R squared to the 1/2. And then I got to take the derivative of that, and that 2 will cancel out the 2 that I got from dividing it by, or from the 1/2 when I took the derivative. So I just get a Z on top. And then when I take the derivative of the absolute value of Z, I'm just going to get 1. So now I can change the order of that and say that it is Q over 2 pi epsilon naught times 1 minus Z over the square root Z squared plus R squared. And that should be the Z component of the electric field. I can again check that by doing stopping share here. We just solved another problem in here, and it was this problem. And we basically got this value right here. Okay. The only difference is they went ahead and factored out. Oh, I left off an R squared. Everybody look at this. Y'all see that R squared down there? That R squared down here was supposed to be here. Here.
You're not sharing.
Here. Sorry about that, everybody. I'm going to fix this now. So I'm going to say, again, an R squared down here. And then I'm going to put my absolute value in that bracket back there, and that'll be there. And in fact, I'll have it R squared right here as well. Okay, so now that works a little better. So anyways, if you look at this does look like the same equation we had, Q over 2 pi epsilon naught R squared. The only thing they did was they used X
Professor,
instead
I'm
of
pretty sure
Z.
you're not sharing your screen right now.
Oh,
I just
okay.
joined, so I wasn't sure if it was something wrong with my screen.
No,
But
you're
I
right.
don't
I
think
just
it's
noticed it,
wrong
it
at
didn't
all.
share. Let me, sorry about that. Thanks for catching me on it though. Okay, so I did hit share, but it evidently didn't go through. I'm gonna try it again now. So remember the equation we had once I added those 2 pi, the R squared down here in the bottom, you can see now it's the same thing, Q over 2 pi epsilon naught. I used R instead of R0, so I got R squared, and I used Z instead of X, so I got Z squared plus R squared 1/2. They ignored the absolute value of X there. That's an arguing point. It's not really that big a deal, but either way, we can do that. So now that I got that, what I want to see is that actually the electric field we expected? Well, I can go back to chapter 21 again and go to my continuous charge distributions, which is, there it is. Scroll down to this section. There's the ring we did a second ago. And here is the infinite charge, uniformly charged disk. There that is. And you see, I get, they're actually framing it in terms of sigma. So just remember sigma would be Q over pi R squared. I have Q over 2 times pi R squared times epsilon 0. So yeah, this is exactly, excuse me, this is exactly the front of what I got. And then I have in parentheses 1 minus Z over Z squared plus 1/2. Or excuse me, Z squared plus R squared to the 1/2 power. Okay, so you can see I did in fact do it correctly. Let me, if y'all want to write that down or just sort of remember what it is, remember the sigma is Q over pi R squared. So when you see mine, I'll have a Q up here and a 2 pi epsilon naught R squared down here, but this will be exactly the same. So I'm gonna stop sharing, put it back on my iPad, pull up my iPad, and of course it won't connect to my iPad anymore because that's just awesome. That's just the way that works. Isn't that cool? So let's do stop share just a second. Disconnect my Wi-Fi. Reconnect my Wi-Fi. Looks like that's working. Open up my good notes. Now I'm going to attempt to share again. And let's hope for it. Yes. Okay. So you can see down here, I did get the same thing. Once you put that little green R squared in there, at least. So obviously that's kind of important. Okay, so Q over pi R squared is just the sigma the book was talking about, but it had 2 over 2 epsilon naught under that. So I've got the 2 and the epsilon naught under that. Then it's got the 1 minus Z over that. So all of this checks other than me dropping that R squared like a crackhead. Okay, any questions on that, everybody? All right, did y'all understand how I did that and how I went through that process of sort of just figuring out a differential charge element? In that case, I happened to use the actual ring as the differential charge element. I didn't actually do it like we did in chapter 21, where I didn't even use the original formula. In this case, I still use the original formula. So of dv or the integral of dq over 4 pi epsilon naught R squared. So any questions on any of that?
I do have a question.
Mhm.
Why is it the absolute value of Z minus the square root of Z squared plus R squared for the
Okay. In the part here where basically what happened was we had to take the limit as R approached 0, or excuse me, not the limit, but we had to evaluate the range at R equals 0 and R equal big R. When I did R equals 0, I had to submit basically in place of the R, which all that was supposed to be little r. Oh yeah, that's what. Okay, I've just noticed another boo-boo. Let's circle that right quick. That was supposed to be a little r. Okay, so when I put little r in there, substituted 0 for it, I got the square root of z squared. So the square root of z squared, that's not a big deal. But once you take the square root of it, you're taking what's called the principal square root, which is a positive value. So technically you cannot get a negative z out of that. So that's equivalent to writing it as absolute value of z.
No, I understand that. I guess I'm confused why it was using the r equals 0 first instead of using the big R.
Oh, that's because I decided to get rid of the negative sign by doing it that way. Remember,
Which negative sign?
yeah, remember we had a negative sign. Actually, let me think. Is that the same one that I ditched the negative sign with? Let me see. Oh no, I didn't do that with this one. So I had 2q over 4 pi epsilon naught r squared. When I evaluate at r, yeah, where did that negative go? V is equal to 2q. That works. That works. U to the negative 1/2. I add 1 to that. That's 2/2 minus 1/2. Would be 1/2. So I get that, and then I divide by 1/2. That puts a 2 on top, and then that should be square root z squared plus r squared minus the r equals 0 case. Yeah, I should have had. It looks like I should have had this in the opposite order. Oh, and I should have. I just wrote it wrong. Thank you for catching that. Actually, I just looked it up in chapter 23. Yeah, I just wrote it in the wrong order. I think I was thinking about that negative thing and made a boo-boo. So thanks for catching that error. Let me do it this way. So what I'm going to do is I'm going to erase this instead of doing the little circle things. God, I mean, a bunch of little minor but pain in the butt errors on this. You're absolutely 100% right. It is supposed to be that other one first. So I am going to write this in blue so they'll see that the work changed a little bit, but it turns out that this should be equal to the square root of z squared plus r squared minus the absolute value of z. Okay, so yeah, you're right on that one. Is that the only concern you had, or was it something else as well?
Oh yeah, I was just confused by that. I thought I was missing like a negative sign.
No, you were right on the money. I don't know where I went with my brain. I might have been trying to get it back in the form that I knew the E was going to be in. I don't know. No telling with me. So sorry about that. And thank you for catching it. That actually saves us a lot of trouble later on, because now I can tell the students exactly what happened and in real time. So that helps. I appreciate that. So that was the charge distribution of basically a disk. Now, one of the things you can do is you can look at that disk and you consider where Z is much greater than R. And I think you see what happens is Z squared plus R squared essentially just becomes Z squared. So we get the square root of Z squared, and that actually goes off like 1 over, or that actually goes off like to 0. But if you really wanted to take the time to work this out to where you got a term that wasn't 0, you could do the binomial expansion or something like that and actually show that ultimately this thing starts to act like a point charge where the distance is r squared. That's a nice technique. The other thing you can do, though, is you can consider Z really small compared to R. And the way you do that is you divide out an R squared, say, and then you'd have Z squared over R squared in the square root plus 1. And of course, that would be under the square root. And that means you could pull the r squared out and it'd be 1 over r squared coming out in the front. With that, you can start to see that it actually becomes infinite because the r squared is going to cancel out and you end up getting sigma over 2 epsilon naught, which is exactly what we expected for an infinite disk. So when you take the limit as z approaches 0, or let's say z is infinitely smaller than r, then it behaves just like sigma over 2 epsilon naught, which is what we found for an infinite plane. So that's the kind of thing you're supposed to do with all your physics results. Each time you solve a problem or derive an answer, you should say, does that make some physical sense in the ranges, say, where it's really close to the object, or in the range where it's really far from the object? Sometimes, like when I tried the really far from the object, you saw that just the first order approximation was z is way greater than r, so the square root of z squared plus r squared just becomes z. Then I got z minus z in the parentheses, so that didn't work at all. That was a bad example. It's not bad. I mean, it's good to try, but in order for you to see the effect, you'd have to go in, look at the back cover of your book, find the binomial expansion, and expand that z in turn, that square root of z squared plus r squared in terms of that. And then you would actually see that it would be more like q over 4 pi epsilon naught r squared. So that's basically it, where q is the total charge of the thing. Now, we've talked a lot and done a lab about the equipotential lines. You can see, for instance, in section 23-5, they have, for instance, a parallel plate capacitor where you have basically one plane that is positively charged and then another plane that's negatively charged. That's sort of the definition of a capacitor, or at least that's the simplest scenario of a capacitor, and assuming they have the same amount of charge on each one. Now, what we did in lab was we would find a particular spot and put the one of the leads of the galvanometer down, and when you did that, you'd say, okay, all the points where the galvanometer reads 0 has exactly the same potential. And when you did that, you got a series of lines like this that went like that. And of course, if you connect them, that makes essentially a straight line here. And then when it gets near the edge, it starts to bend out. A similar line here, a similar line here, and a similar line here. And this would bend out as well, and this would bend out as well. Okay, those are equipotential lines. And of course, a conductor is the equipotential surface. And one of the things that we learn about that from Gauss's law is that the boundary conditions that are defined by Gauss's law tells us that the electric field at a static situation next to a surface of a conductor has to be perpendicular to the conductor. So the electric field is going to be perpendicular to it. And its value is sigma over epsilon naught. Because if you actually do Gauss's law, the inside of the little soup can is in an area where there's no field. In a static situation, there's no electric field inside the conductor. Your book talks about all this, but knowing that, we can say, okay, well, this electric field has to leave perpendicular to the equipotential, to the surface of the conductor, because that's an equipotential surface. And then it's got to be perpendicular to all these equipotential lines. And then it's got to be perpendicular to this surface. Then it's just a matter of realizing that positive charges would be compelled to run to the right. So we can say the direction of the electric field is to the right. And in fact, if we take the voltage from one of these to the other and subtract that, divide it by that distance between them, we will get the magnitude of the electric field. So if we actually knew what voltage those equipotentials are, we'd get that. So that's sort of what we're talking about with equipotential lines and surfaces. The equipotential lines are sort of analogous to contour lines on a contour map. So in here, we get here, but out here, you can see it comes off this way, then it's got to go like this. Then it's going to go like that. So the electric field, as you get near the edges, do start to fan out a bit, but generally between them, they're a nice uniform magnetic field, or excuse me, electric field. We'll talk about magnetism soon enough, I guess. So we've talked about how to calculate the electric field. Once we have the voltage, we just take what's called the negative gradient of V. That's another thing to let you know. When I say E is equal to negative del V, that's called the gradient of V. And it's a way of making a scalar into a vector. You'll learn that the gradient is actually something that comes in handy in Calc 3. Hopefully, you'll probably get at least this far. You don't normally get to surface integrals and line integrals in Calc 3, but you do get to gradient, or you get to the generalized chain rule, where you might have a function that is not only a function of several variables, but you actually might have several functional field that has several functions of several variables. And when you go to do a derivative of that, you have to use the chain rule, which includes a gradient. So I just wanted to point that out to you. That's called the gradient. This is called the divergence. And this one, remember, is called the curl. Okay. So section 23.8 talks about electrostatic potential energy. And again, that's basically using the idea that I will break off this right here and here and here. Okay. We know that delta U is equal to UB minus UA, in other words, U final minus U initial, which is equal to Q times VB minus VA, which you can also just call Q delta V. So if you calculate the voltage, for instance, due to a point charge when you're some distance R12 away, then that voltage V would be equal to Q1 over 4 pi epsilon naught R12. In other words, if I bring a charge Q2 nearby, then I would call the distance between 1 and 2 R12. So that now the potential energy, when I bring that other charge in there, is in fact equal to Q2 times V. So I end up getting Q1 Q2 over 4 pi epsilon naught R12. So that's the potential energy of two charges collected. Now, if I want to do, let's say 3 charges collected, then I'm going to have a scenario where I get like U is equal to Q1 times Q3 over 4 pi epsilon naught times R13 plus Q2 Q3 over 4 pi epsilon naught R23. And of course, we still have the original one, which was Q1 Q2 over 4 pi epsilon naught R12. So you can see these things starting to act up. And if you're trying to keep your wits about you, it's not that easy. You need to come up with some way of doing it neatly and making sure you count everything. So you fall into the rut of making sure you go 1 and then hold 1 constant and hit all the other things. 1 with 2, 1 with 3, 1 with 4, 1 with 5, 1 with 6, 1 with 7. And of course, you're never going to hit 1 1 or 2 2 or 8 8. So you do that. Well, when you come to row 2, you're going to hit 2 say 1. Well, you've already counted that because you did that 1 2. So you got to keep track of all that. But other than that, that's ultimately what the potential energy is due to that. I did talk about the electron volt. So that was all that was covered in section 23.8. So I just wanted to hit on that a little bit. You guys can read that over. Really, the major thing I want to do now, we did talk about the electron volt. That's covered in here. There's an example in it that's pretty straightforward. I think I might have even done one of those. I'm not messing around with the digital binary. There might be some in the homework, but I'm probably going to choose to leave those out in the actual testing. I'm going to leave out the noise and transmission. I'm going to leave out the TV and computer. I wholeheartedly want you to read it so you can do better on the homeworks and the conceptual questions and stuff like that. And just for your knowledge, but on the actual test, not the practice test, but on the actual test, you will not be tested on it. Okay. So they talk about oscilloscopes and electrocardiograms, everything like that. Okay, this is the one thing I wanted to make sure I got with you, and that is section 23.6, which is the potential due to electric dipole. I know I'm not sharing the screen with you. I just want to let you know that. But if you imagine in this case, let's say we have an electric dipole. Actually, I don't want that. I want the straight line. Okay, so let's imagine we have an electric dipole, and that electric dipole is a charge of, let's say, negative Q, and then another charge of, say, positive Q. And let's say their distance apart is D. Okay, and now we're imagining at a point really, really, really far away, though my drawing doesn't allow it to look that far away. There's a line connecting the positive charge to the negative charge. And I'm going to say it's this line. And then there's a line connecting the negative charge and the point P, like that. Boy, that turned out bad. Okay. Now, if I draw a line that's actually perpendicular to that left one and runs into this right one, I can say that, oh, that's not very good. Didn't go perpendicular enough. Looks more like this, say. Yeah, that looks pretty good. Okay, so this is actually perpendicular here. And in fact, now you have R and R are both the same distance. Okay, but this quantity right here is going to be called delta R. And we can call this angle right here Q, or excuse me, theta. Okay. So if I want to calculate the electric potential at P due to this, what I'm going to do is say V is equal to positive Q over 4 pi epsilon naught times R plus negative Q over 4 pi epsilon naught. Make sure I put them on the right side. Yeah, I did everything on the right side. Okay. And this one is going to be at R plus delta R. Okay. So that's sort of what we got, and they sort of look alike. So I can simplify it by taking out the Q over 4 pi epsilon naught, and even taking out, say, no, I'll leave the R. Yeah, I'll leave the R. And what I have left is 1 over R minus 1 over R plus delta R. Okay. Now, in principle, we'd like to simplify this. So one way we could do it is we could multiply the numerator and the denominator of the leftmost fraction by R plus delta R. And then the right fraction, we could multiply the numerator and denominator by R. And that would give us V is equal to Q over 4 pi epsilon naught times. Now I'm going to have R plus delta R over R times R plus delta R. And then minus, I'm going to have R over R times R plus delta R. Okay, now I got a common denominator. And when I do those, of course, that's going to become R plus delta R minus R. So ultimately I get Q over 4 pi epsilon naught. Notice I have a common factor of R in the bottom, so I can go ahead and put that here. And then I can take and say that I have delta R over R plus delta R. So that is actually a expression. Now you can consider a scenario where, let's say delta R, or let's say R is much bigger than delta R. That's a very normal situation when you're really far away. So if you say R is much greater than delta R, then you can simplify this and get something along the lines of V is equal to, if you notice the triangle down here, delta R is actually equal to L times what? Cosine theta. So I can say Q times L, or excuse me, times D, sorry about that, times D times cosine theta, because that's what delta R is. It's actually equal to D times cosine theta. So that gives me my Q and my delta R, and then R plus delta R is essentially just R, since R is so much bigger than it. So it's going to be over 4 pi epsilon naught R squared. And you probably recognize that symbol Q times D. That actually is the dipole moment. So we can actually just call this P cosine theta over 4 pi epsilon naught R squared. So one of the reasons we did all this is I want you to see something that has been going on with dipoles. So when you have a dipole, it's not quite the same as having a point charge, because you have a point charge of Q that gets you a electric field of Q over 4 pi epsilon naught R squared, right? If you have a dipole, though, you have a charge of Q and then another charge of minus Q. So that's got to weaken it some way. It's got to make it a little less weak, a little less strong than just a single plus Q. And in fact, what you find out is if you calculate the electric field, which normally goes like 1 over R squared for a point charge, when you calculate that a really far distance away from a dipole, you get that the electric field goes like 1 over R squared, or R cubed, excuse me. So E for electric dipole is on the order of 1 over R cubed. And now what we're seeing is, in fact, the voltage, which is normally on the order of 1 over R for a point charge, the voltage is in fact proportional to 1 over R squared when you're really far away from a dipole. So that's sort of the point we're making, is that it, and it should make sense that it does this, but it in fact is tempered by the presence of an opposite charge. So that's about it. That's all we really needed to cover from this chapter. Next chapter, we go into capacitance, where I'm going to take that V equals the negative integral of E dot dl, and I'm going to use that to actually calculate the capacitance of a parallel plate capacitor. I'm going to use it for calculate the capacitance of a coaxial cable. I'm going to use it to calculate the capacitance of, let's say, what we call a solenoid, and also what we call a toroid. And a solenoid is basically, if you remember taking a nail and wrapping a wire around it to make an electromagnet, if you pulled, or if you left the nail in there, it would be okay too. But if you pulled that nail out and just left the wire in that nice, neat coil like you did, that coil is a solenoid. And yeah, sometimes they allow you to put, I mean, you can put a piece of metal in the solenoid for an added effect. So it wouldn't be a terrible thing to leave the nail in, but that's something that could be done. Now, if you take that solenoid and make sure it's really, really long and curl it into a donut, that's a torus. So we're going to attack an infinite plane, infinitely long coaxial cable, and then we're going to get a solenoid, and then we're going to do a toroid, which is again a donut. So that's what we're going to do with the capacitance. We're also going to learn how capacitances behave in circuits. Turns out they're sort of the opposite of resistors, where resistors in parallel, the net resistance becomes the sum of the two. and resistance in, resistance in series, the net resistance becomes the sum of the two, but resistance in parallel, the reciprocal of the net resistance is is the sum of 1 over the resistances. Well, it turns out capacitances are just the opposite. So capacitances in series add like reciprocals. In other words, 1 over Q total is 1 over Q1 plus 1 over Q2 plus ... And weirdly enough, capacitances in parallel add. So you got Q totals equal Q1 plus Q2 plus Q3. So we'll learn that. And eventually we'll get to AC circuits where we can learn all that other cool stuff too. So does anyone have any questions before I let you guys go? All right, well, I'm going to wait for the last person to split. Everybody's free to go. Remember, you got homework assignment due just about every Sunday. So, all right, yeah, you guys meet on Thursday. So just about every Monday, you got a homework assignment due. So make sure you get the homework assignment due done. I think you have a test coming up that's due on Monday as well. So make sure you get that. But that's chapters 21 and 22, not 23. But make sure you do the practice test a bunch of times. If y'all have any questions, y'all can, of course, email me. I check the email at least once a day on weekends. If it's something urgent, you can send me a text. I usually, I'm always checking those. So if I decide that it's urgent when you send it to me, I'll probably reply as soon as I see it. So you're free to go. Thanks for coming, everybody. And now everybody will see me do my Forrest Gump wave. Bye-bye. Bye-bye. AJ, are you still here, or do you have questions, sir? All right, it looks like AJ is not here. I do not see evidence of him typing any chats in or anything, so I'm going to say night night. See you, everybody.